There is a uniform spherically symmetric surface charge density at a distance r0 from origin. The charge distribution is initially at rest and starts expanding because of mutual repulsion. The figure that represents best the speed v of the distribution as a function of its instantaneous radius rt. Okay, so basically in this problem there is a spherical symmetric charge distribution which can be considered like a spherical cell, and that is expanding because of the mutual repulsion. So let me show you the profile here. So this is the initial configuration when the charges are at a distance of r0 initially, and from here it is expanding because of the force of repulsion. So this sphere radius is increasing. So this situation is similar to balloon, which is initially uh, there is no air in it. Now if we blow air within the balloon, you will find that the balloon is basically expanding as we feel air in it because of internal air pressure. It keeps on expanding. So same thing here because of the repulsion pressure, electrostatic repulsion pressure, or you can say electrostatic repulsive force, this is expanding. At any moment its radius is rt. Now here we have got that idea that what is happening. Now what, how to approach this problem? So because this is an isolated system, so we can think of conservation of energy and conservation of momentum. So first of all, I will say that initial momentum is 0, so every time momentum has to be 0, and this is a symmetric distribution. So I will say that the radius, it is expanding in all directions symmetrically. Like when you are filling air in the balloon radius is increasing symmetrically. So all the particles are moving symmetrically in all directions, so that the momentum sum of individual particles will add up to give you 0 value. Second point is the conservation of energy, because this is an isolated system, so total energy of the system will be conserved. Now here initially total energy is available in form of self energy only, that is kq squared by 2r0. But as it expands, so its self energy is decreasing, and because of that system acquires some amount of kinetic energy. So here this is the initial energy kq squared by 2r0. Then we have final energy, that is kq squared by 2rt, that is the self energy plus the kinetic energy. All particles have the same speed, and so if I integrate the mass of all the particles, I will get total mass m. So half m v squared. Now I will conserve the energy EI equals to EF, and after conserving the energy, if I substitute it, I will get the value here. And then on rearrangement, we are going to get V square equals to this one. So if we talk about V, then what we get here, V equals to KQ square by MR0 minus KQ square by MRT. So this is the value of V that we have here. You can see that with the time r is increasing, so this term is decreasing, so overall this term is increasing. So with the time v keeps on growing. So if we have to choose best option from this one, I will discard this 3 because it is increasing than decreasing. But what we have seen, it keeps on increasing, and then when r becomes infinite, this term becomes 0 and this becomes constant. Now if you see the option 2, you will find that the speed is skyrocketing. It keeps on increasing, keeps on going higher and higher as the R increases. So basically this is also not satisfying the mathematical relation that we have. Now in between first and fourth we have to check. So you can see how we can differentiate these two graphs. So these two graphs can be differentiated on the basis of slope, because here I can see there is a continuous variation in the slope and the slope keeps on decreasing. Here you can see slope is increasing, then maximum, then it is decreasing. So to get the slope, dv by dr we have to calculate. Now we know v as a function of r, so I will differentiate it. Okay, I will differentiate this function here. So when we differentiate this function, so in that case this will become, let's differentiate this part. So v square differentiation with respect to r will be v into dv by dr. We can write 2 here also, no problem, we can write 2 here, and then this will become kq square, this will be 0 and minus kq square by mrt, and rt differentiation will be minus of 1 by rt square, minus minus will become plus. So here you can see that dv by dr, if I further add this value d dv by dr, there is a 2, okay, that is missing here, so I will substitute in the last kq square by mrt square, and if I substitute the value of v here, then you focus this thing that as rt is increasing, okay, v is also increasing. So here v is in denominator and this is also in denominator, and both are increasing. So if both are increasing with time, then this overall term is decreasing. When overall term is decreasing, that means slope is also decreasing here. Slope is also decreasing here. So I will, if I check the slope of the graph, I will say that in this graph I find that the slope is continuously decreasing, and in this graph slope is initially lesser, then it is greater, then it is decreasing. So the correct option is option 1. Option 4 is incorrect here.